In this module, we can discuss about the mechanism of IR and Raman spectroscopy. The input ray, the electromagnetic wave, as acted as an input ray, is impinged on the atomic level. But there is a small vibration or rotation in that particular level that is going to be generated, the vibration and rotation spectra from that molecular dimension. The generated energy are in quantized level. So in this second diagram shows that there is one type of electromagnetic ray is possible to vibrate the triatomic molecule. During the triatomic molecular vibrations, but there is a three types of electronic transition. One is electronic transition is possible, and the rotation energy and also vibration energy is possible. Rotation energy is nothing but a small vibration energy is nothing but a one single line spectra, but rotation energy you have the fine structural line spectra. I should record on here. Okay, so in what way that type of spectrum has been analyzed by using these studies? We can discuss in detail in this. But let us discuss in detail today is introductions and about molecular spectroscopy, followed by IR basic mechanism, laser Raman basic mechanism, and what type of instrumentations has been developed by using this particular mechanism, and finally summary of the today's idea. In introduction part, what about we discuss about the spectroscopy is a study of interaction of electromagnetic radiation with the matter. The matter is in the any form consists of molecules. You can note that the matter is consist of molecule which undergo rotation and vibration under excited conditions. Okay, but during that interactions of the electromagnetic wave in that particular dipole moment, the absorptions of the electromagnetic radiation in rotation spectrum of molecule arises from the interaction of molecular dipole moment with the electromagnetic field. So in this diagram shows that there is a one type of heterogeneous molecule that is called the dipole is to be connected with internuclear distance is going to be one of the spring-like nature. But during the interaction of the radiation with the matter, the type of springs is going to be vibrated back and forth. That vibrations is uniformly distributed that particular energy level that like a harmonic oscillator generations. From that one electronic level to another electron, there is so many number of electronic levels has been takes place during that rotations of that molecules. So these are the basic idea about that. So one is called absorption, and the next one, the first diagram shows absorptions. In that absorption, that is called a ground state of electronic level. That is called excited state. From the ground to excited position is called absorptions. There is a small transition times that we reside at the particular excited state. Once again, it comes to that ground state. But during that transition, there is a small emissions of molecules is going to be possible. So that is to be recording inside the orbital or excited level. That's all information about the excited level of that molecule. Okay. So in this way, you just getting the absorption spectra has been developed. There is a small energy is going to be applied to the particular ground system that like a red color symbol that electron is to be shifted from n equal to 1 down to first excited state. If your the energy is increases, the energy is increases, the electron is getting shifted to our next excited state, and blue is should be shifted from n equal to 1 to n equal to 4. Okay, so in this way there is absorptions of energy is possible. Okay, but during that absorptions of energy due to the interactions of that radiation, The energy is to be produced as such as rotational, vibrational, and translation modes are created. But all energies are quantized. The generation of this energy during the rotation, vibration, as well as translations, the energy is quantized. Basically, the transition time for rotation and vibration levels. Rotation and vibration is simultaneously happening inside the molecule whenever the interaction between the electromagnetic wave. Okay, the transition time is 10 power minus 14 to and 10 power minus 12 seconds respectively. The meaning of the term is there is 100 vibrations are recorded in one single rotations. Okay, but there are center of symmetry or non-center of symmetry molecules will be available in nature. So center of symmetry molecules is nothing but example is homonuclear compounds. This is oxygen, hydrogen, nitrogen, etc. Okay, and also the heteronuclear compound is called non-centronuclei. That's called HCl, methyl alcohol, as well as water is called non-centrosymmetry molecule. So if you have to apply the infrared ray, there is a interaction between the infrared ray and the dipole moment of that heterogeneous molecule. This way, the molecule has been rotated or vibration in the excited state, but it should be inactive for centrosymmetry molecules. Okay, the molecules possess a dipole moment permanently. The vibrations or rotations is possible in the molecule. If you have to apply the IR rays, IR to the molecule, there is absorption and emission of the signal. Particular molecular vibration is existed. In linear molecule, there are 3n minus 5 vibrations are created. On non-linear molecule, 3n minus 6 vibrations are created in the forming of either absorptions or emission spectra, respectively. So, this is actually one the figurative denoting that it's a dipole. The positive and negative charges should be separated through some distances called dipole. So this is actually dipole moment is nothing but a q into the r. Q is a charge of the particular particle or electron. R is the distance between the two charged particle. Okay, the q dot r is called the dipole moment. So this is actually the natural dipole moment is be possible from that water molecule that's called two hydrogen and one oxygen is be connecting. There is a dipole moment is going to take place inside the molecule. So that's where the dipole moment is reacted during the interaction of IR rays in the particular molecule. So this is commonly IR spectroscopic instrumentation technique. The first of all, that source is to be acted in that particular filament is producing IR rays by incandescence lamps. That incandescence lamps is to be producing the IR signal to the sample. The sample during that the molecular vibrations, so that's called a heterogeneous molecule. The heterogeneous molecule is going to be vibrated or rotated. This type of signals is going to be using for diffraction grating and finally detecting that particular signal by using the detector. Okay, this is a basic idea to make an instrumentation, so FTIR spectroscopy. So the FTIR spectroscopy, this block diagrams is shown here in that way. This is actually IR sources to be given. There is a 45-degree two convex two lenses going to be used. It automatically that IR rays is be produced. One is putting on the sample, another one is going to reference. So the reference is actually KPR sample is used as a references. The IR sample, the signal is to be compared in this area, and finally that's going to be splitting of this splitter, and also finally there's got a detecting the signals and the processing the signals. Finally, that's the display of that particular signal. So these are the vibrations of that. There's the standard vibrations of the molecular. So this is actually fingerprints below 1200, below 1500 cm power minus 1, cm power minus 1 during that absorption spectra. Below that level, there is a fingerprint of the molecular vibration is possible in that level from 400 to 5500 cm power minus. So below 400, we cannot be detected. but IR spectra resolution is 400 to 4000 cm power minus 1. And after that 1800 to 500 to 1800 cm power minus 1, there is a functional vibrations. C double bond C, C double bond N, and C double bond O vibration is recorded here. And also the triple bond can vibrations can be detected from 2100 to 2300. About 2800 is CH vibrations as called, and above the 3200 is called water molecular vibrations, is called OH vibrations is possible in that recording of spectra. It should be recorded here. These are typical spectra for IR element, IR spectral lines. So this big symbol denoting that absorption spectra. So you compare it the wave number, and also that a particular element is going to be presented here. So from that the compositional studies, that's called structural studies also, and also the compositions has been presented in our particular sample, is going to be were discussed by using the spectra. So some of the active elements, some of the centrosymmetry elements do not active by the IR spectra. That particular signals cannot be fetched through that diagrams. So we cannot determine the particular signals to be presented in FAR. Next, we discuss about the Raman effect is nothing but a scattering phenomenon. If the source of the incident molecule, the output ray consists of the Rayleigh scattering and some lines of interaction energy between the input of the molecule. Hence, the molecule gaining energy and some lines are losing energy is Stokes and anti-Stokes lines are recorded on either side of the Rayleigh scattering lines. Stokes and just analyzing that a particular Stokes lines, it should be some frequency shift from Rayleigh Rayleigh signals. That signals is a shifting of that particular left side signals is exactly coincidence to the particular vibration and rotational spectra of the molecule. So the Stokes and anti-Stokes lines is uniformly distributed on either side of the Rayleigh scattering, that like a mirror image of that Stokes and anti-Stokes lines with respect to the Rayleigh scattering. So the Rayleigh, during the scattering phenomena, there will be a much more informations are getting from that molecular vibration than dipole vibrations. Okay, so this is actually the typical Raman Stokes lines. That's called this some of the excited lines that were commonly used as a mercury as an excited source in the earlier days. So that when we go to recording that particular excited source of that single spectra, even though in the single spectra they have the more number of times. So that you have to replacing by the excited source by the laser Raman laser spectra. So during that laser spectra, there will be a exact, there will be a very single amount of time, very frequent amount of time, and there's so many number of spectra is going to be recorded. So from that left side is going to the Stokes lines, and from the right sides, 4B cm power minus 1 is uniformly separated from the one signal to another signal. That's called anti-Stokes lines. The Stokes lines is gaining of energy during the interactions of that laser Raman to that molecule. It's a losing of energy during the interactions of that molecular vibrations. So it will give the more information about the particular rotational and as well as rotational and vibration spectra of that particular molecule during the molecular polar stability conditions. This is a typical diagram for scattering of light. So here the incident light is incident on the particular nuclei. There are so many number of scattered particles there. So each one of the scattered particle it will be recorded, and they got to finalize each one of that scattered molecule will get the more information about the particular molecular vibration and rotation spectra, comparatively to the IR spectra. So this is actually the incident light is be passed through that. particular molecular vibrations. Then molecular vibrations is going to be exactly matched to the incident rays called Rayleigh scattering. Something about the frequency is lower than the incident ray is called Stokes line, and something is greater than the incident light is called anti-Stokes scattering. So these are the some typical Rayleigh as well as Stokes line scattering from that energy level that could give generating the virtual energy states during that transition. They can be created the virtual energy states during the transition of the Raman signals. So before that, we can go to the summary of the idea. The spectroscopy is nothing but the interaction of radiation with the matter. Molecule may be in any form. During that interaction, rotation and vibration of energy exists in the excited state of matter. So in the interaction of IR, whenever the molecules in a heteronuclear level, the molecule are vibrated or rotated during the interaction of IR with the dipole moment of the molecule. In Raman spectroscopy, the molecule rotation are matched the Stokes and anti-Stokes and during the inelastic scattering. That is called a molecular. That's nothing but a molecular polar stability conditions. So, so from that I conclude my talk about the mechanisms of IR and Raman spectroscopy. Thank you.